So in this video we are going to discuss the question in thermal and statistical physics which appeared in JRF June 2014 examination. The first question is, which of the graphs below gives the correct qualitative behavior of the energy density E lambda of a black body radiation of wavelength lambda at two different temperatures T1 and T2 such that T1 is less than T2. Okay, so here we can predict the behavior of the graph with the help of Wind's displacement law, which says that at any particular temperature lambda into T, that is equal to constant. Okay, so here lambda is the wavelength corresponding to maximum energy density. Okay, so for instance, if I plot a graph between the energy density versus temperature here, that is E lambda as a function of temperature, as a function of wavelength at a certain temperature. Okay, so the graph will appear something like this. Okay, so the area under this curve that will give the total energy density at that particular temperature contained in that particular body. Okay, so this lambda corresponds to the energy wavelength corresponding to the maximum energy density. So this is also called as the minimum wavelength at which there is a maximum energy density. Okay, so when the temperature of the cavity is changed, okay, then this curve shifts toward the lower wavelength. So then the maximum in the energy density will occur at higher lower wavelength. Okay, and then its behavior, it's something like this. Okay, and the point is that at a higher temperature the energy density within the corresponding to black body radiation that's going to maximum at higher temperature when compared with the lower temperature. So therefore with these 2 points in mind, because T2 is larger than T1, so that means lambda, the wavelength corresponding to maximum energy density at temperature T2, this will be at smaller wavelength as compared to wavelength at temperature T1. Okay, so therefore if we just take a look at the graphs here, so option C satisfies this condition. Okay, so T2, because T2 it's at a higher temperature, T1 is at low temperature, here the corresponding wavelength, it is this one, this is lambda T2. Okay, lambda T2, and here for the temperature T1 it is lambda T1. And also if you just take a look at the area under the curve, it is smaller for temperature T1 and it's larger for the temperature T2. So therefore option C is the correct one here. Let's take a look at the next problem. The statement is, a system can have 3 energy levels with energy 0 and plus minus E. So let's first draw the corresponding energy levels for this given problem. So we are having a system with 3 energy levels and the energies are, so minus E, 0 and plus E. Okay, it's given that the level E0 is doubly degenerate. So here the degeneracy of this level is 2. So that means others are given to be non-degenerate. Okay, the average energy at inverse temperature beta is, so here beta it is 1 by kVT. Okay, now we can solve this problem by making use of the partition function approach. Okay, so the partition function for the system is given by, so let's call the partition function as Z. Okay, so that is equal to sum over all state Gi exponential minus beta Ei and I. Okay, so this is equal to G1 exponential minus beta E1 plus G2 exponential minus beta E2 plus G3 exponential minus beta E3. Okay, so let's call this as G1, this is G2 and this is G3. Okay, so this is equal to 1 exponential minus beta E1. E1 is minus E, so that will become positive. So 1 exponential beta E plus G2, which is 2 exponential minus beta, which is 0, E2 is 0. Okay, plus G3, that is 1 exponential minus beta multiplied by E. So after rearranging all these terms, this becomes 2 plus exponential beta e plus exponential minus beta e, and that is equal to 2 plus 2 times cos hyperbolic beta e. Okay, so that's our partition function, or this can be rewritten as 2 into 1 plus cos hyperbolic beta e. That is the partition function. So let's call this as our equation 1. Now from here we can immediately determine the average energy of the system by making use of the relationship E, that is equal to minus curly beta of ln z. Okay, that is equal to minus curly beta logarithmic of 2 into 1 plus cos hyperbolic beta e. So that is the average energy. So upon differentiation with respect to beta, so this will give us the average energy, that is equal to minus 1 upon 2 into 1 plus cos hyperbolic beta e, and then its differential with respect to beta. So that is equal to 2 multiplied by 1 plus 2 multiply 1 plus it will be 2 into sine hyperbolic beta e, 2 into sine hyperbolic beta e, and then again the differential of beta e with respect to beta, so that will give you e only, because beta will be gone with respect to differentiation with respect to beta. Okay, so now upon rearranging all these terms we will obtain, so this is equal to, so 2 will cancel with 2, okay, and this is equal to minus e sine so I can write sine hyperbolic beta e as 2 sine hyperbolic beta e by 2 multiplied by cos hyperbolic beta e by 2 divided by 1 plus cos hyperbolic beta e is equal to 2 cos hyperbolic square beta e by 2. Okay, so again 2 will cancel with 2, okay, and then the cos hyperbolic beta e by 2 will be cancelled with cos hyperbolic beta e by 2, and we will be left with minus e tan hyperbolic beta e by 2. Okay, so that is the average energy for this system. So therefore option D is the correct one here. Let's continue with the next problem. The problem is the free energy F of a system, it depends upon thermodynamic variable psi as with the given equation, which is F, that's free energy, that is minus A psi square plus B psi 6, where it's given that A and V, they are greater than 0. The value of psi when the system is in thermodynamic equilibrium. Okay, so when a system it's going to be in thermodynamic equilibrium, so in that case the free energy is bound to satisfy this condition, that is dF upon d psi, that should be equal to 0, and at the same time its second differential with respect to psi, it should be greater than 0. So that's the condition for the stability of a system. Okay, now we will apply this condition in order to obtain the desired value of psi here. Okay, so dF by d psi, dF upon d psi, basically we are minimizing f with respect to psi, where psi is it's also called as the order parameter. So dF by d psi, that is equal to minus 2a psi plus 6b psi 5, and that should be equal to 0. Okay, so after rearranging these terms, so we obtain 6b psi 4, that is equal to to A. So psi that will become common and it will come outside. Okay, so here if we substitute, so that means what I can do is I can write psi 4 that is equal to A upon 3V. Now if I take psi square that is equal to T. Okay, so this means I can write this as T square is equal to A upon 3B, which implies that T that is equal to plus minus A by 3B power 1 by 2. Okay, so that means because T it's equal to psi square, so which indicates that psi will be equal to plus minus A by 3B power 1 by 4. So therefore C is the correct option here. So let's continue with next problem. The statement is, for a particular thermodynamic system, the entropy S is related to the internal energy U and volume V by the relationship. So let's first write the relationship. S, this is equal to C U power 3 by 4 V power 1 by 4, and it's given that C is a constant here. Now we have to evaluate the Gibbs potential, which is defined through the relationship G that is equal to U minus Ts plus PV. So we have evaluate its value. So what is the value? Okay, so basically to find G we require the value of T and P, because the value of entropy is given to you and we will keep it as it is. So the value of T and P can be calculated with the help of the thermodynamic potential, the change in internal energy du that is equal to TdS minus PdV. Okay, so this relationship implies that temperature can be evaluated, temperature that is equal to du by ds by keeping volume constant. So when you keep the volume constant, this term will disappear and T will be du by ds. Okay, and similarly pressure can be calculated from this relationship, pressure that is equal to minus du by dB by keeping entropy constant. Okay, and let's call this as relation 3. Okay, now because temperature that is du by ds, or sometimes the temperature can also be evaluated in other way around by making use of the relationship 1 by T that is equal to ds by du. Okay, so it doesn't make any difference in the evaluation of this parameter. So okay, so for making use of this equation, what I'm going to do is I'm going to invert this equation. So that means I will write u on the left hand side. Okay, so by inverting equation 1, so what I obtain is u power 3 by 4 that is equal to S upon C B power 1 by 4. This implies u is equal to S power 4 by 3 divided by C power 4 by 3 and B power 1 by 3, and let's call this equation as equation 4. So therefore we can easily evaluate T that is equal to du by ds by keeping other parameters constant, so that in volume constant. So we will make use of equation 4 for evaluating du by ds. So it's only the differential with respect to s, so I can keep other terms outside. So 1 upon C power 4 by 3 B power 1 by 3, and then differential of s power 4 by 3. Okay, so that will give us 4 by 3 s power 1 by 3. 4 by 3 minus 1, so that will give you 1 by 3. So here we will substitute the value of s from equation 1. Okay, so then we will obtain the final result for temperature T. So that is equal to I'm keeping 4 by 3 in front, so 4 by 3 divided by C power 4 by 3 B power 1 by 3, and then replacing S power 1 by 3. So S power 1 by 3 will be how much? It will be c power 1 by 3 and then u power, it's already 3 by 4 and its power 1 by 3, so that means I can multiply the powers. Okay, and then v power 1 by 4 and its power 1 by 3, so that means I can multiply it. Okay, so some of the terms in the numerator and denominator, they will cancel with each other, and at the end what we will obtain is, for instance, c power 1 by 3 will cancel with the c power 1 by 3 in the denominator, and then we will be left with the c power 1 only. Okay, and similarly the u power this will become u power 1 by 4 in the numerator, and okay, and also b power 1 by 3 will cancel with b power 1 by 3 in the denominator, and we will be left with only b power 1 by 4 in the numerator. Okay, so that means after rearranging all these terms, so this comes out to be equal to, I'm writing the final expression here after rearranging these things. So this is equal to 4 by 3 and then c in the denominator, okay, and then u power 1 by 4, because this will cancel with this one, that's u power 1 by 4, okay, and then v power 1 by 4. Okay, so now let me call this as equation 5. Okay, so now we have calculated T. Now we want to find the expression for the pressure. So pressure is minus du by dV. Okay, so minus du by dV, so that means minus outside s power 4 by 3 divided by c power 4 by 3 and then curly b of 1 upon b power 1 by 3. Okay, and this is equal to minus s power 4 by 3 upon c power 4 by 3 and then differential of v. Okay, so minus 1 by 3 outside and then v power minus 1 by 3 minus 1. Okay, so here, so that is equal to, after rearranging all the terms and settling all the parameter, 1 by 3 s upon cv power 4 by 3. Okay, and this can be rewritten as 1 by 3 s power 4 by 3 divided by c power 4 by 3 b power 1 by 3, okay, and then multiply by 1 by v. Okay, now what is this equal to? S power 4 by 3 upon c power 4 by 3 into b power 1 by 3, that is equal to u, equation 4. Okay, so that means what I can do is I can write pressure, that is equal to 1 by 3 of u by v, 1 by 3rd of energy density. This is also one of the standard results, so let's call this as equation 6. Okay, so now we have obtained the expression for the temperature as well as pressure. So now we can immediately find the value of G, that's the Gibbs free energy or Gibbs potential. So that is equal to U minus Ts plus PV. So here we will substitute the value of T and P and then we will see what we are obtaining. So U minus T, so T is equal to 4 by 3C and then u power 1 by 4 divided by b power 1 by 4 and then the value of the entropy S. Okay, so this quantity multiply by C u power 3 by 4 b power 1 by 4. So u minus Ts plus P into B. P is how much? That's 1/3 of energy density. 1 by 3 u by b, okay, into V. Okay, so V will cancel with V, it's u by 3. And here again some of the terms will cancel here, so this will become equal to u minus 4 by 3, okay, So here if you just see various terms will cancel with each other. B will cancel with this one. So this is u power 1 by 4 into u power 3 by 4. So that is equal to u power 4 by 4. That is nothing but u. Okay, plus u by 3. So after adding we will obtain that this is equal to 0. So therefore C is the correct option here. Let's continue with the next problem. So the problem is the pressure of a non-relativistic free Fermi gas in 3 dimension depends at t is equal to 0 on the density of fermion n as. Okay, so here we are going to make use of the results corresponding to the electron gas which is confined to 3 dimension and its parameter at absolute 0. Okay, so at absolute 0, absolute 0 Kelvin, a Fermi gas or the electron gas, you can say E gas. For the Fermi gas in 3D, the Fermi energy is given as EF, that is equal to h cut square upon 2m multiply by 3 pi square n by b power 2 by 3. Note that here n is the total number of electrons, that's in the electron gas, which is a Fermi gas basically, and v is the volume where these n electrons are confined. So we can write small n to be equivalent to the number density of the free electron. Okay, so let's call this as equation 1. Okay, and for this system, for this Fermi system, the pressure and energy density are related as pressure is equal to 2/3 of energy density. So this result is valid for the non-relativistic system. Okay. Okay. So now the average energy per fermion, E average, this is connected with the Fermi energy by this relationship. That is equal to 3 by 5 EF. Okay, so now the total energy can be calculated from this E average, that E is the total energy of the system, that is equal to the total number of fermion in the system multiplied by average energy per fermion. Okay, so that is equal to 3 by 5 N multiplied by EF. Okay, so let's call this as equation 3. Now the pressure is, it's a 2/3 of energy density, pressure is 2/3 of E by V. So let me write 1 by V outside, and E is equal to this expression. So E, that is equal 3 by 5 into N EF. So 3 will cancel with 3. So this is nothing but 2 by 5 N by V multiplied by EF. So that's the upper expression for the pressure exerted by this Fermi system at absolute 0. Okay, so this can be written as P, that is equal to 2 by 5 N by V, that's the number density, and then multiply by the Fermi, the expression for the Fermi energy, which is equal to h cut square upon 2m into 3 pi square N by B power 2 by 3. So now from here we notice that pressure is proportional to N by V and its power 1 plus 2 by 3, and that is nothing but that is equal to N power 5 by 3. Okay, so therefore A is the correct option here. So pressure depends upon the energy density as N power 5 by 3. So let's continue with the next problem. The statement is, in one dimension, a random walker takes a step with equal probability to the left or right. Okay, so we are given that here P, this is equal to Q, and that is equal to 1 by 2 for taking steps either to the left or right. Okay, so for example, suppose a random walker is at this point in the beginning. Let's call this point as origin. Okay, and suppose the random walker is taking its first step along the right hand side. Okay, and let's say it's taking its next step along the right hand side again. Now in order to come back to the same starting point, now the random walker has no option other than to take the step in the backward direction and take the 4 steps also in the backward direction. Okay, so that means in total, so it's only possible that when the walker is taking same number of steps in the both direction. Okay, so that is the steps to left are equal to the steps to the right. So that means here n1 is equal to n2, that is equal to 2. Okay, so the corresponding probability P R, where R is equal to 2, that's the steps to the left or to the right, R is equal to 2, that is given by, that is equal to n is the total number of steps, NCR, and then P power n1 or so called R, P power R, and then Q power R, because here n1 is equal to n2, that is equal to 2, so that's why we are writing here the same exponent for P as well as for Q. Okay, so the corresponding probability will be 4C2, and then because P is equal to 1 by 2, its power 2, and then Q is also equal to 1 by 2 and its power 2. So this after evaluation will give us 4 factorial upon 2 factorial and then 2 factorial and 1 by 2 power 4, and after doing the calculation this is equal to 3 by 8. Okay, so therefore A is the correct option here. Let's take a look at the next problem. The statement is the van der Waals equation of state for a gas is given by P plus A upon B square into B minus B, that is equal to RT. Okay, now where P, V and T represents the pressure, volume and temperature respectively, and A and V are the constant parameters. So at the critical point where all the roots of the above cubic equation are degenerate, the volume is given by. Okay, so in order to handle this problem, we must have an idea that what we are going to do is we are going to take the first and second order differential of pressure with respect to volume, and then we are going to equate those differential with equal to 0. But before we do that part, let's try to understand why we take the differential of pressure with respect to volume. Okay, so if you just talk about the a real gas, okay, and plots the isotherm, so that means a graph between pressure and volume, okay, pressure and volume, okay, at constant temperature. So at higher temperature the curves will look like this, okay, something like this. Okay, but as you keep on reducing the temperature, a situation will arise that here the curve will start deviating from the ideal gas curve. Okay, so here we will have a point of inflection here, and with the further reduction in the temperature, a situation something like this will appear. Okay, so the temperature at which the deviation from the ideal gas behavior occur, we call that particular isotherm as critical isotherm, and the corresponding temperature at which such kind of behavior is noticed, we call that temperature as the critical temperature, and that is written as Tc. Okay, so at critical temperature a point of inflection, we notice a point of inflection here. Okay, so in order to determine the parameter corresponding to this point of inflection, so basically what we do is we take the differential of P with respect to B, and then we equate that equal to 0. Okay, and that's how we can find the corresponding parameters. So the corresponding pressure is called as the critical pressure, and the corresponding volume we call as the critical volume. Okay, so that's the reason behind taking that derivative. Okay, so after differentiating this equation once, so we obtain the value of one critical parameter, and then we can substitute the value of that parameter back in this equation, and then solve it again, and then again it's a derivative. Okay, so that the second derivative, so if you join these two points of inflection, so we obtained a curve something like this. So the equating side second derivative equal to 0, so that is d2p upon dv square, that is equal to 0. So that means what we are doing is, again we are talking about this point. Okay, so joining all these points we obtain this curve, and then again we are taking its differential to obtain the parameters corresponding to this point. Okay, so mathematically let's see how we can determine these PC, BC and TC. Since in the question we are only asked to find the value of the BC, that's a critical volume, so we will not do the calculation for the other parameters. But once the value of one parameter is known, so immediately we can obtain the value of other critical parameters also. Okay, so let's see how we will proceed. The equation of state for the van der Waals gas, that can be rewritten as P, that is equal to RT upon B minus B minus A upon B square. Okay, let's call this as equation 1. So at critical point, or at critical point, that is at T is equal to TC. So as I said earlier, we call this as critical isotherm. Okay, so at this point, dP by dB at T is equal to TC, that is equal to 0, and also d2P upon dB square at T is equal to TC, that's equal to 0. Okay, so dP by dB zero, that is equal to minus R TC upon Vc minus V, its square plus 2A upon Vc cube, and that is equal to 0. So I will call this as equation 2. Okay, so after rearranging this equation, we obtain RTC upon Vc minus V square, and that is equal to 2A upon Bc cube. Okay, so I will call this as equation 3. Okay, now again differentiating the equation with respect to V we obtain. So that means basically we are going to differentiate this result again. Okay, by removing the suffix C here. Suffix C here, it simply denotes that we are talking about the critical the parameters at this point, that critical corresponding to the critical isotherm. Okay, so again differentiating equation 2, we will obtain d2b d2p upon dv square corresponding to T is equal to Tc, and that is equal to 0, which is equal to 2RTC divided by Vc minus V cube minus 6A upon Bc4, and that is equal to 0. Okay, and after rearranging this result, we obtain 2R Tc divided by Vc minus V cube, and that is equal to 6A upon Vc4. So let me call this as equation 4. Now what we will do is we will divide equation 4 with equation 3, which implies, so some of the terms will cancel, and after dividing these two equations, we obtain 2 upon Bc minus V, and that is equal to 3 upon Vc. So after solving, this will gives us Bc, that is equal to 3V. So that means the critical volume is nothing but it is 3B. So that is our answer. So here D is the correct option here. Let's continue with the next problem. The average local internal magnetic field acting on an Ising spin is given as, okay, so here we are given the average local magnetic field as H internal, that is equal to alpha m, where m is the magnetization and alpha is a positive constant. So that's given to us. Okay, at a temperature T which is sufficiently close to and above the critical temperature Tc, the magnetic susceptibility at zero external field is proportional to. So because we are talking about the magnetic susceptibility, so that means somehow we have to bring into the picture the external field V. Okay, let's try to understand this problem. So here the general Hamiltonian for the 1D Ising model is general Hamiltonian for 1D Ising model is H is equal to minus summation of I and j si dot sj, and then minus b summation over si. Okay, so the Hamiltonian contains two terms. Okay, so I'm going to explain these two terms in a moment. Okay, so here j, that's the spins, j is the exchange integral basically, that represents a spin interaction. Okay, so j, it is positive for ferromagnetic interaction and j, it is negative for antiferromagnetic interaction. Okay, so here first term represents the, so the first term, it represents the nearest neighbor interaction, nearest neighbor interaction. Okay, and SI is the individual spin at each lattice site. Okay, the second term, it represents the sum over all lattice sites. Okay, sum over all lattice sites, and it represents the, the external field V, external, it represents the external field B trying to align all spins in one direction, so which is the field direction of field in one direction. Okay, so H can be rewritten as H the Hamiltonian, this is equal to, basically we are doing this exercise to just to look for the interaction energy, and once the interaction energy is known to us, then we can immediately write the partition function for this system. Okay, so H can be rewritten as H is equal to minus sum over I and j. Okay, j into si sj minus b si, and that is equal to minus sum over I, so I'm taking si outside, and inside the bracket we are left with sum over j. Okay, and then j sj plus b. Okay, and this can be further rewritten as, this is equal to minus si as it is, and then inside the bracket I'm writing alpha m, that's the internal field. Okay, I'm going to explain it in a moment, plus b. Okay, let me call this as equation 3. Okay, so here what we have done is we have replaced this j si sj terms with the alpha m. Okay, it represents the, this term represents the average effect at each site due to nearest neighbors. Okay, so now the interaction energy the expression is known to us. Now we will try to write the partition function for this system. Okay, so the partition function can be written as Z, that is equal to sum over Si exponential minus beta and multiply by the Hamiltonian of the system, and that is equal to Si equal to plus minus 1 to n exponential summation Si and then beta, because it's beta here, and then multiply by alpha into m plus b. Okay, as Si can take two values, that there are two values which are feasible for Si, so that means Si, it can take two values, okay, either plus 1 or minus 1. Okay, so therefore the corresponding partition function for one object, so that is equal to exponential, so we will have only two terms, okay, one corresponding to S1 Si equal to plus 1 and another one corresponding to minus 1. Okay, so that is equal to exponential beta into alpha m plus b plus exponential minus beta into alpha m plus b. Okay, and that is equal to 2 cos hyperbolic beta into alpha m plus b. Okay, so let's call this equation as let me check the number. So up to 3 we have already given the number, so let's call this as equation 4. Okay, and for the n spin system, this can be rewritten as, for n spins, this is equal to 2 cos hyperbolic beta into alpha m plus v and its power n. So this is equation 5 here. Okay, now the magnetization can be calculated as the magnetization okay, m, that is equal to minus curly a by curly beta. Okay, and this is equal to n by beta curly beta of ln z1. Okay, and this is equal to nkt nkvt. So beta I'm writing it as 1 upon kt, nkt, and then curly beta of ln z1. So curly beta of ln z1. So what is ln z1? So this is this expression. Okay, so ln into 2 cos hyperbolic beta into alpha m plus b. Okay, and this is equal to, after the differentiation, so n kt, k is basically the Boltzmann constant, and divided by 1 upon 2 cos hyperbolic beta into alpha m plus b, okay, into 2 sin hyperbolic beta into alpha m plus b. Okay, and then multiply by beta, and this is equal to beta, that's 1 upon kt, and okay, so this after rearranging all the terms, so what we obtain is m comes out to be equal to n tan hyperbolic beta into alpha m plus b. Okay, so let's call this as equation 6. Now here we will make use of the fact that close to the transition point, so this equation 6 gives us the magnetization. Okay, so now close to the transition point, higher order terms in m will be very small. Okay, so that is, we can approximate tan hyperbolic x to be approximately equal to x minus x cube by 3, so on, where x is much smaller than unity. Okay, so we can also ignore the this cube term. So therefore 6 can be written as, so therefore 6 reduces to 6 implies that magnetization under this approximation, this is equal to magnetization, that's approximately equal to beta into alpha m plus b plus higher order terms. Okay, or what we can do is m, after rearranging all these terms, m into 1 minus alpha beta, that is equal to beta into b. So this implies m upon b, which is the susceptibility basically, that is equal to beta upon 1 minus alpha beta. Okay, and this is nothing but 1 upon 1 by beta minus alpha, or this is equal to 1 by beta minus alpha power minus 1, or that is equal to kbt minus alpha power minus 1. So therefore from here we conclude that the susceptibility, that is xi, that is equal to m by b, that varies as this expression kt minus alpha power minus 1. So let's take a look at the options which are given to us. It is kt minus alpha power minus 1. So therefore C is the correct option here.